So now I am going to talk more specifically about the code I have given to you for the option 1. So the code is linked from this section in the Git repository here. And you should carefully the readme file under this 21 mnist directory. So this video is basically following the instructions in this readme file. So this program trains a neural network for handwritten character recognition, or actually a digit recognition, I should say. So the code is a very basic implementation without vectorization, parallelization, or a GPU implementation of whatsoever. So the specific model implemented is actually a C++ translation of MNIST model in the PyTorch examples. So you can look at the PyTorch examples here. So this is the entire Python implementation, and the model is actually described here. And the original PyTorch model is obviously written in Python, but my implementation is purely C++ that does not rely on any external library. So you can easily get how it exactly works. And you may want to run the original PyTorch implementation, or just for the later comparison, and also to get a sense of how the learning should progress. So this can be done by just doing these commands. So let me first log in the Taulex server, and let me bring up the screen command and do this command to download the PyTorch examples. And in the examples, you have the mnist subdirectory, and this main.py is the implementation. So you can simply run the implementation by this. And it does everything from downloading the data and training. So training is going to take some time, so leave it alone and go ahead. So this is how you can download my baseline C++ implementation again from the GitHub. So you just copy this command and execute it. So you have this directory, and the mnist implementation is here in this 21 mnist. So data set is under this data directory. So you have training images, training labels, test images, and test labels. But you don't have to know much about how this data is actually formatted. And here's how you can compile. So it just at the top level directory, you just type make. And by default, it builds the two executables. So one is something called the mnist CPU base. The other is mnist CUDA base. So CPU base is obviously a baseline implementation for CPUs, and this is obviously for CUDA. But it can actually run on CPUs too. So just type the executable name just to run it. So it does almost the same thing as the PyTorch implementation. So you can immediately notice that this baseline implementation is actually much slower. By the way, so just take a look at how many CPUs the Python implementation is using. So it is actually using a lot of CPUs. So it is seems using the all of the CPUs presumably. Whereas in my implementation, it is, well, again, the baseline implementation with the parallelization or whatsoever. So it's only using 100% CPU. So it's not surprising that it's actually much slower than the Python implementation. So this is the default behavior of my implementation, and it's almost identical to the PyTorch implementation. So data is written, so read from this data directory. So this is somewhat different from the Python implementation, but you end up reading exactly the same data. So it runs 14 something called epochs. So a single epoch corresponds to scanning the entire training data set once. So 14 epochs means that it scans the entire training data set 14 times. And training data set actually contains 60,000 images. So it ends up with processing 840,000 samples in total. The mini batch size, the number of samples used at a time to update weights, is 64. And every 10 mini batches, it reports the loss of a mini batch. So if you take a look at this, so it reports the progress every 64 by 10 samples, 640 samples. So between epochs, it scans the entire test data set, which contains 10,000 samples once, and report the accuracy. So you can take a look at it from the PyTorch command. So this is when the PyTorch command reports the accuracy against the test data set. So it already achieves, well, almost 100% accuracy against the test data set. So actually, there's not much point in continuing learning any further. So there are some runtime options implemented in my C++ implementation. So you can run the help option, um, some other options. Let me skip them. So one thing that is useful, especially when you developing your code, is so the option that specifies the batch size, the mini batch size, or the number of samples taken at a time. So for example, if you specify -b1, so it is taking only a single sample at a time. So there's a hard-coded parameter that is a maximum number of batch size, because it determines the size of the structure used in the program. So you can change this parameter, the maximum number of batch sizes you can specify with this option by specifying this max batch size in the command line and compile the executable again. So the way you can actually do it is modifying the make file. So search for this max batch size. So if you change this option to something else and compile it again, so make clean will remove the executable and compile it again. So you have the max batch size equal 128. So you can specify a larger batch size. So you can also specify the number of iterations to run. So you can control the length of the execution. You can also change the number of data used both for training and test. So they are also useful for controlling the length of the execution. So for example, this is a way you can get an extremely short execution time. So you use only a single sample as a training data set, which is of course meaningless, but just for the sake of shortening the execution time, and especially for debugging, why it may also, still be useful. So set the training data set size to 1. You also set the test data size to 1, and you run only a single iteration. So this one finishes yeah, almost instantly, like this. So these two options, initialization seed and dropout seed, for seeding random number generators used internally in the implementation. So this initialization seed, or more specifically weight seed, affects how weights are initialized. So this is essentially the seed given to the random number generator. And there are two layers called dropout. I didn't explain it in details in the earlier video, but so this is a layer um, that takes a number of inputs and produces a same number of outputs. And for each input, the output may be 0 or the same as the input, and it, either one is chosen randomly or probabilistically. So those seed options specify the seed for the random number generator that chooses which inputs will be 0. So you don't have to know too much about how these seeds are actually used, but the only thing that is important here is that, so unless you specify these seed parameters, the initial weights and which inputs are dropped are exactly the same when you repeat the same command line. So what I mean by that is, for example, if you run this command twice, so the first time the loss is something like 2.32, and after processing 160 elements, it's something like this. So if you do this command again, the trajectory should be exactly the same, like okay, 2.32 in the first iteration. In the second one, yeah, this one looks exactly the same as this one. Right, this is what I mean by that. So, well, actually, you don't have to know too much about um, the how these are actually used internally. But the only thing is that so if you run the same command without these options, or giving exactly the same seed for each uh, option, the trajectory should be exactly the same. So this should be the case after you modify the code. So this is actually very helpful for debugging. So if the program behaves differently each time the same command is run, the way it is very difficult to debug. And the other important thing is, okay, so after you think you have done correct implementation, you should give a different seed just to make sure that you are code works for any initial weights or for any dropout patterns. So there are other options like choosing the directory and controlling the learning rate, and these are not particularly important. So the other important option is this dash A. So first of all, this version MNIST CUDA base compiled by NVCC can run the GPU version, like the CUDA version more specifically. And as a matter of fact, it is the default that automatically happens when you run this MNIST CUDA base. So let me show you how this works. So the log into the other server supporting GPUs, and so if you run this MNIST CUDA base, so let me give it a small batch size parameter. So it is running on GPU using CUDA. And even if it's running on CUDA, it is using only one single CUDA thread, so it's very slow. And this version actually can run on CPUs too by giving this dash A CUDA, dash A CPU base option. So by doing this, so it is now running on CPU. So we are comparing a single thread CPU versus a single CUDA thread. So CPU single thread is actually much faster. But that's not the point here. So the other one, the MNIST CPU base, has this CPU base is actually the default. So this one and we're explicitly giving dash A CPU base, it is actually exactly the same. And if you run this, so the MNIST CPU base with dash A GPU base option, then yeah, it simply fails. So it's not supporting a GPU base option. It says that invalid algorithm. So just to summarize what this dash A option is for the baseline implementation. So there are two algorithm choices, so CPU base or CUDA base. And CPU base obviously runs on CPU, and CUDA base obviously runs on GPU using CUDA. And the one compiled with Clang++ called the MNIST CPU base, well, by default it is equivalent to giving dash A CPU base. And if you give the CUDA base, well, it's an error, so it does not support CUDA. The other one compiled by NVCC named MNIST CUDA base. So by default it is equivalent to giving dash A CUDA base. But you can also give dash A CPU base to run it on CPUs. So the same binary can support multiple algorithms. And this is indeed a framework with which you can implement your own algorithm. So essentially, when you implement your own version, where you are adding another algorithm choice as the parameter, as the argument to this dash A option. So I get to that point again later. But so let's say you somehow manage to load your own version. So you wanna make sure that you got it done right. So when you, for example, implement your own version of backward propagation, so you may be afraid that you broke that function. So you want to make sure that you at least get the mathematics right. So for that purpose, so you probably want to start with something like this after you implement your own version. So let's say, okay, so the binary executable name might also be different, but let's say it is the same binary name, MNIST, CPU base, and you give your algorithm at the argument to your to the dash A option. So you wanna get started with giving a very small parameters for train data size and test data size. So specifically, this uses only a single training sample and no test data at all. So it keeps taking a single data and updating the weight for that particular data or the sample. So the display the loss value when the learning progresses. So they are down, they are here. So it should quickly decrease and it should quickly become nearly zero. So you should observe something like this, starting from somewhere around 2.3. After a few iteration, it should become almost zero. So when it doesn't happen, yeah, something must be clearly broken. So this is definitely the first thing you have to do after you roll your own implementation. And after making sure that this indeed happens, well, the next thing you want to do is try it with somewhat larger batch size, but still a bit, no, not necessarily a batch size. So somewhat larger train data size and train test data size. Um, so you want to make it larger, but still maintain them to small numbers. And so you want to gradually increase the number of data used. So by the way, so if you're curious about what does this loss value actually mean, here's how you can interpret it. So in the so if you remember what is the loss value of this particular network in the explained in the earlier video. So you might remember that in the final stage of the network, so there's a layer called the softmax. So that the softmax output vector of 10 components or 10 elements, so which is the number of classes for each image. That each component of the vector represents the probability that the model thinks the image belongs to a particular class. So let's call this 10 element vector P. Um, this the 10 element vector P is then compared with the true label. And if the true label to class of that image is a C, then the actual loss for this particular image is computed as negative log of PC. PC is uh, prob the probability output by the network uh, that a particular image belongs to the true class, the correct class. And so in the very early stage of the network is actually a sort of a random guess. So that returns the probability 1 over 10 for every class. Then the average loss for a single image is likely to be somewhere near negative log 1 over 10, which is log 10, which is something like 2.3. So it is not a coincidence that in the early iteration, the loss is almost always close to 2.3. So this should be the case in your implementation too. So in the very beginning, the loss should be something like 2.3. So if this is not the case, you are likely to have broken something. So this is how the baseline code basically behaves. Now I start talking about how you start your own work. So the first thing you want to do is probably to get familiar with the source code so that you can have some ideas about which part of the source code should be modified. Of course, you can directly look into the source code. So this is a top level directory and this is a top level file. And all of the important source files are in this include directory. So there is, for example, uh, convolution.h that implements convolution layer, a linear.h that implements a linear or free connected layer, and there are some other files like dropout.h, maxpooling.h. But well, rather than directly looking into the source code by yourself, here are some helpful web pages that are generated from the source code. So one is this Doxygen. So you have all these source files, and you can look into any of them. And so there are some documentations about each function and each data structure. Like, for example, in the case of convolution.h, so there's a class called convolution 2D, and you can dig further into this structure, and you have many methods implemented in this class. So this is one way you can look into the source code. Oops. And the other helpful source of information is this web page. So this is showing the source code itself, but in the form of web pages. And each one has a link. For example, if you click on this, which one I should click? For example, if I click on this, you can jump to the definition of this MNIST data structure. So this MNIST data structure has fields called conv1, rel1, conv2, and you can navigate yourself to the definition of, for example, convolution 2D. So this way you can navigate the source code itself just by following the links. And the last but not least, perhaps the most important way to familiarize yourself with the source code, or more in more general how everything works, is to compile it with this debugging option and without any optimization to help debug more easily, and run it under the debugger, either GDB or CUDA GDB. So this is indeed a very powerful method to look into the source code of some unknown programs. So let me demonstrate how you actually do it. So the first thing you have to do is to change the compile option. So just modify the make file. So instead of this dash O3, so you have dash O0 dash G, and compile it again. So you can do it outside the editor and do something like this, or you can do it inside the Emacs actually. So I am gonna do everything inside the Emacs. So now you have two executables inside this exe directory. So before you run it within the debugger, you want to make sure that it correctly runs inside the exe directory, because GDB actually tries to run it under exe directory anyway. So make sure that it runs within the exe, which apparently is. But the one thing you have to know is that there must be a data directory in the current directory, so the directory from which you run this command. So there must be this symlink to the data directory. So if you remove this symlink, then yeah, it fails to load the data. So remember that the original data directory is the the top level directory here. So if you go inside the exe, well, there's originally no data directory. So I just made a symlink to the directory one level above to make sure that it runs correctly inside the exe directory. So now you are truly ready to run it within the uh, debugger. So the way you do it within the Emacs is something called metaxgud gdb. Then you specify the name of the executable you wanna run, like this. So now actually there's an issue. So it says this error, dwarf error, DW form, blah blah blah, which I don't understand. But the important thing is the debugger complains saying there's no debugging symbols found in the MNIST CPU base, which shouldn't be the case if I gave the dash G option. But there is apparently an issue with GDB and CRAN. So if you just Google this error message, um, so I found this page. So GDB older than 10.1 can't need Krang's debugging symbol format called dwarf v5. So this page actually suggests giving this dash g dwarf 4 option instead of dash g. So let me do it. So instead of dash g, you wanna give dwarf 4. But actually this option is only necessary for Clang++. So if you give this option here, this same option will be given to the other compilers like NVCC, which actually doesn't work. So instead of giving it to the flags, so I give it to the Clang++ specific flags. So here, and then compile it again. So this time, instead of going outside the Emacs again, so let me compile it within Emacs by doing this. So here again, I got two executables. So we are finally truly ready to run it within the GDB. So let's, oops, so this is actually the same thing as before. So let me quit the GDB once and do it again. So this time it says it successfully read symbols from this executable. So this is the indication that it is now working. So so I strongly recommend you to learn the GDB yourself in this opportunity. So in this video, obviously I cannot teach everything you need to know about the GDB. So you have to learn by yourself. But so the minimum things you have to know just for the purpose of this demonstration. The first thing is this run command just to invoke the executable. So it starts normally like when you do it from within the shell. So by the way, this one is much slower than what you have seen before, because this time I gave the dash all zero option that turns off almost all optimizations. And well, so if you simply run this command using run command of the GDB, well, it simply start from the beginning to the end, which is not particularly useful. So the actual way you want to do with debugger is, so before you run this command, you set the breakpoint at the beginning of the main function. So B is for breakpoint. So this says, okay, so when the execution reaches at the beginning of the main function, you should stop. And then you issue this run command again. So then the program stops at the beginning of the main. So from here, so instead of running normally, so you execute one line at a time. So let me make it somewhat taller. So n is the command for executing until the next line. So if you press n here, so the execution stop at the beginning of the next line. So you keep doing this. So just to repeat the previous command, you simply type the enter. So I'm like doing n many times. And okay, so these are apparently not necessarily significant things, like start logging and seeding the random number generators. Here's the code giving the configuration options for each layer. So this line might be important. This is the line where you instantiate the MNIST network. And the next line is apparently initializing the weights inside this network. But let me keep pressing N, just skip the initialization method too. And okay, this is where you are reading data from the data file. So let me skip over them too. So actually, this is where the real thing starts to happen. So you repeat the specified number of epochs, train, and then test. So train is, well, obviously the very important function. So you want to look into this function rather than executing until the next line. So to look into this function, you press S. S stands for step. step into the function rather than next or n. So let's press S. Then you are inside this train function. So again, so you keep pressing and until you reach the next important function you wanna look into. So this is a loop that loops over all the samples in the data set. So you get data. So actually B samples at a time. So this B is the batch size or the number of samples in a mini batch. So the specified number of samples will be loaded into X for input and T for true outputs. And indexes are for just indexes for samples. And after you get the mini batch into X and T, you do this well function. You do this function that looks obviously very important, forward and backward, and then update. So let's look into this function or method. So what is happening inside this forward, back, and update is, so first you call forward, then call backward, and then update to update weights. So let's look into this forward function by pressing S at this line. So now, yeah, what is obviously a very significant things happening. So you call a forward function on each layer. So convolution 1 followed by ReLU 1, followed by another convolution and ReLU. And then you call max pooling, then a layer called dropout. So FC stands for fully connected. So it is essentially a linear layer, followed by another ReLU 3, followed by another dropout. Then another fully connected layer, and then negative log likelihood softmax. So this is exactly where yeah, the real evaluation of the function is happening. So by the way, so let me show you that this is exactly what the PyTorch implementation is also doing. So convolution 1, ReLU convolution 2, ReLU maxpool, and blah blah blah. So this code was simply a replication. So my code is simply a replication of this this code. So let's look into the forward method of this convolution layer. So you will be seeing what I explained in the earlier slide. But before the real thing actually happens, so this is an important function you want to understand when you implement your own version. So this is essentially a dispatcher. So it does appropriate things based on the given algorithm parameter or the argument given to dash A option. So if it is a CPU base, it calls the CPU base version of this forward function. And if it is a CUDA base, then it calls forward CUDA base function. So you are going to add your code here. So another case here to dispatch this function into your own version. So you do this for every layer you are going to implement. But for now, so it is obviously a CPU-based version. So it is dispatched to this forward CPU-based function. So let's look into this function. Then it simply calls another function, forward base. Well, so it is apparently doing something very meaningless. But the reason why things are structured in this way is actually the forward base is used both by forward CPU base and forward CUDA base. But this is not super important here. So let's look into this forward base function. So this is where the things that I explained in the slide uh, is actually happening. So yeah, this is a very deeply nested loop computing the value of each output pixel by something like this. So essentially taking the inner product of two uh, vectors. So you look at this code and you compare this code with the slide I have explained earlier, which is this. So in terms of the picture, it looks like this, but in terms of the mathematical expression, the convolution can be expressed like this. So when you carefully look at this expression is exactly the same as what this code is doing. You can confirm it by yourself. So everything actually looks almost exactly the same, no matter whether it is CUDA version or CPU version, or no matter whether it is convolution or linear layer or something else. So if you keep pressing N to execute this entire uh, very deeply nested for loop, it takes ages. So there must be a way to finish this function. So this is a finish command of the GDB. So if you press fin or fini, the execution goes until you return from this function. So then press N again to exit from this function. Keep pressing N, go to back to this um, forward function again. So just to show that things are structured in almost exactly the same way in all layers, let me uh, look into the forward function of ReLU. So again, this code is almost exactly the same as forward function of convolution layer. But I am we are actually looking at another um, class or another file, even if the method name is the same. So again, it is dispatched to the forward CPU base function, which again simply calls a forward base function. And inside the forward base, you have something like this. So yeah, it is again a deeply nested loop, but what it is doing on each pixel is much simpler. It is simply taking the maximum of 0 or the original pixel value. So this is exactly what ReLU function should be doing. So again, continue execution until this function finishes. And keep pressing and to get back to the forward function of the entire MNIST again. So let's skip the rest of the layers. So by pressing N. By the way, so convolution, the second convolution layer is taking much time, especially when it is compiled without any optimization or with dash or zero option. But still keep pressing N until the entire thing is finished. So now we are out of forward function. And then we are now in the backward function. So backward function was the traversing all the layers in the opposite order. So you can understand this by earlier slide. So by understanding how gradients of uh, the loss with respect to each intermediate variable is calculated. So let's first look into the backward function of this NLL softmax layer. But again, the structure of the code is almost the same as before. And again, this time it is dispatched to a backward CPU base function, which then calls backward base function, which is now doing the real thing. So again, you can confirm that this piece of code is exactly what it's supposed to do by comparing this with the slide I explained earlier. So let's finish this function and get back to the backward function of the entire MNIST. So let's keep doing. So let's keep skipping the inside of these functions until you finish everything. So, well, so the other thing you can notice by running it with debugger is which layer is taking most time. So obviously this convolution 2 is the layer that is going to be most significant when you optimize things. But anyway, so let's finish this entire function. So now you are going to update weights. So actually the layers we need to update weights convolution two convolution layers and linear layers. So other layers do not have weights to update. So let's look into the update method of update function. Yeah. So again, the structure is almost the same as other functions forward and backward. And again, so you are dispatched to update CPU base, which simply calls update base, and this update base calls update function of the each layer that needs to be updated. So inside this update function, well, actually you are calling the update function of this other delta optimizer. So this is actually where things are a bit different from what I explained in the earlier slide. So in the slide, I explained something called SGD, which is actually the sort of the simplest kind of way to update method based on the gradient you calculated. So you can learn about this other delta by looking at this page. So there's a pointer to other delta. So this is how other delta works in mathematical terms. So this is the gradient you calculated by the backward phase, and this gradient is used in this way. So the details are not very important, and I didn't explain why this is a good way to update weights. But just understand that this piece of code is doing exactly what this mathematical expression is specifying. So, omitting details, let's just keep pressing N. So we updated both weights and biases. So you do the same thing for other layers. So this finishes the entire forward, backward, and update cycles for a single mini batch. And so you simply repeat this until you scan the entire training data set. So, like I said, the training data has actually 60,000 samples, and you process 64 samples at a time. So, actually, this for loop repeats almost 1,000 times. So with that, let me finish the demonstration of GDB. So like I said, I strongly recommend you to master GDB with this in this opportunity. So if you are not familiar with Emacs, of course, you can use the same thing within VS Code. So whether you are using Emacs or VS Code shouldn't matter very much. So with that, let me get back to the this instruction. So this is the general guide for developing your code. So which is already partly addressed in the demonstration. So this is the top level main file where things get started. So and important files are actually in include directory, and there's a single header file for each layer. And there are some small things like tensors, so which is essentially defining a multi-dimensional arrays. So some CUDA stuff and some very simple utilities. But you don't have to look into each of them. So you um, learn which part is important by following the execution with debuggers. So, so like I demonstrated using the debugger, well, these three functions are actually very important, forward and backward and update. And these are functions you are supposed to work on. So you are supposed to develop your own version of. So, your main job in this exercise will be to implement a high performance version of these functions. So, three functions for convolution and linear, because these are layers that have this update function, and two functions for the other four layers, ReLU, Dropper, max pooling, NLL, log softmax. Oh, so sorry, this should be NLL softmax. But as I already hinted with debuggers, well, convolution layers will be the most time-consuming part. So at the very minimum, you may be able to have a meaningful speed up just by optimizing convolution layers. So forward and backward at the very least. So here, this page explains the structure, the basic structure of these forward, backward, and update functions, like I have already demonstrated using the debugger. So I don't have to explain it again in this. So. So specifically, how to add your own algorithm. So first thing you have to do is to introduce a new symbol that represents your algorithm. So let's say you name your algorithm as CPU awesome. Well, so in reality, you wanna have a more meaningful name like CPU SIMD or CPU OpenMP or CPU SIMD OpenMP or something like that. But let's say for the purpose of illustration, you call it as Argo CPU Awesome. Then the first thing you need to do is just inside this mnist you have you define the new symbol that represents your algorithm. So just add the line below. And let the program recognize your algorithm. So this should be done inside this pass algo function. So it is another function inside this mnist So this is a simple list of string comparison to fixed string constants. So if you have uh, your own version named CPU awesome, then you simply add another else if branch like if string comp as CPU awesome, then you return algo CPU awesome or something like that. So in some cases, you might want to change the function called algo is CUDA function, so that this program correctly recognizes whether it is a CUDA algorithm, the algorithm that is uh, supposed to be compiled, supposed to be executed in the CUDA environment. So the default implementation actually looks like this. So if the algorithm name uh, begins with CUDA, then it is recognized as a CUDA algorithm. So normally you don't have to change this as long as you are sticking with this naming convention. So any algorithm that begins with CUDA is recognized as such. So this is a setup. So now, so you are ready to add the real work. So after you introduce a new symbol, CPU awesome, then you can add your own case branch inside the for the backward and upgrade or whatever. And the algorithm given in the command line through -a option will be available in this variable. So you execute the switch statement based on the value of this algo. And if this is whatever symbol you introduced, then you dispatch to your own function. So this is the function you are supposed to implement by yourself. Of course, you can start by copying the baseline implementation. Take the baseline implementation and, for example, add vectorization or add parallelization. And in the case of CUDA algorithm, you can do your own CUDA implementation. So yeah, CUDA implementation works almost it is structured in almost exactly the same way. So you can get the idea of how it actually works by following the execution by debugger yourself. So I don't think I have to go into this. And so here are some additional tips that are very helpful when you debug your own code. So one is how you catch a very basic coding errors. So this compile time option dash the array index check is very useful. So what it does is to check indexes given to array accesses in the right range. So this happens every time you access an element of a vector, matrix, or tensor. So by turning this option on at the compile time, whether the program will catch obvious errors such as looping with long bounds or indexing arrays with long variables. So after you finish the implementation of a layer, well, you are very recommended to compile your program with this option on. So the default is this array index check is 0. So you give this option instead. But again, this makes the program very slow. So you do not want to do it all the time. And also, when you turn it on, you wanna run your program with small number of samples in a mini batch. And let's say so you somehow screw up the implementation of this convolution layer, where so intentionally introduce some array uh, indexing errors like this, and compile it. So make sure that this array index check equal 1 option is given. And when you run this code, so it catches array index errors like this. But this isn't necessarily very helpful to know where exactly the error happened. So again, running it within the debugger is very useful to know where the error actually happens. So let me demonstrate it. So this time just run it and let it run until the program causes an error. And at this point, you can show the stack trace of the program. So which part of the program you are executing. And well, actually, the program will stop deep inside uh, the nested program calls, and you simply move the stack frames upward until you reach somewhere you actually wrote. So this is actually inside uh, this range check function, which is actually called here. So this is a method to access a single element of a multi-dimensional array. So you further go up the stack frames, and then you get the exact line at which the error actually happened. So at this point, you might want to check the value of each of these variables by typing P. P stands for print. So this shows the value of this OC variable, and PIC showed the value of IC. So these are apparently within the range, obviously. So you go ahead and print DI and DJ. So now DJ is 3. So if you know that DJ should be less than 3, well, so but by the way, so K is actually 3. So well, so you obviously we intentionally introduced introduce the error here. But doing something like this, you can know which variables is actually out of the range. So this is very useful after you finish the initial coding of a particular layer. So another type of errors you might commit during the development is so-called logical or mathematical errors, which is that your code, well, at least runs until it finishes. So it is not causing any array index errors, or it doesn't crash in any other ways. But still, the it doesn't do what it's supposed to do. So the loss doesn't increase in the same way as other implementations. So just to make it easy to debug that kind of errors, the first thing you might want to do is something like this. So run this with a very small number of training data. So especially just set the training data size to be 1, and you don't use the test data at all. So like I said earlier, so this command processes only a single sample repeatedly. So the error should quickly decrease from something around 2.3 to near 0. So if it doesn't happen, so you clearly introduces a bug. Another thing that is very useful to know is that, like I said earlier, the all algorithms should behave exactly the same unless you give different random number seeds. So if you do not specify any seed parameters, they process exactly the same data and start from exactly the same initial weights. So as long as, for example, when you change the implementation of a particular layer, as long as your implementation of that particular layer does exactly the same thing as the baseline implementation, that the program you ended up with should behave exactly the same as the baseline code. So this is very useful for debugging. So in particular, for example, the initial loss value should be, well, the loss value printed should be exactly the same between the baseline implementation and your algorithm. And also, if you look into the value of the data while using debugger or simply by printing these values, well, they should be exactly the same too, because you are processing exactly the same data with exactly the same weights, right? So, well, except in the cases in which the accumulation of rounding errors might be slightly different, that may make some differences especially in the later stage of the execution. But at least in the first iteration, where everything should be, well, almost identical. So this will help you debug your code tremendously, where you simply compare the values computed by the baseline implementation and the values computed by your algorithm. The other thing very useful to know is that each layer is actually implemented in a single header file, and actually each layer can be compiled into a standalone executable. and that standalone executable has a entry point corresponding to its layer name. For example, in the case of convolution.h, it has an entry point called a convolution main. And if you compile this convolution.h with the definition that convolution main equal main, then this function is going to become the main function, which is the entry point of the executable. And you can get the executable that runs only on this particular layer. So this can be done by simply going into this include directory and run make. So this command just does this for all layers. So you will obtain many executable in the exe directory inside this include. So let me just show you that it happens. So go to include and then say make. Then it's going to compile each of these header file into a standalone executable. Okay, so let me do it again using the parallel make. So it's gonna finish much more quickly. So now you get many executable under this exe directory. So again, let me make a symlink to the data. No. So this one does not need any data. So if you run a particular executable, so it is actually checking the backward propagation. But backward phase is apparently correct. So here's how this check is actually done. So let's say the function implemented by a particular layer is f of w and x. So w is the weight and x is the input to the layer. So f of wx is exactly what the forward function does. And each of these standalone executable, the entry point, the convolution main for the case of in the case of a convolution layer, well that does something like this. So it generates random inputs and random weights, and it generates some small changes to the both inputs and weights. And it tries to compare this value and this value. So these two values will be obtained by running the backward phase. And these values will be obtained by running forward phase with slightly changed weights and inputs. And the difference between this term and this term should be approximated by this one. So this can be easily confirmed by the definition of gradients. So essentially, each of these standalone executable is checking whether this equation is approximately true or not. So this is shown here. So this term and this term obtained by backward propagation are shown here. So essentially these terms. And L minus represents this one. And L plus is this one. and it is taking the difference between L plus and L minus, and say it was this value. And on the other hand, it also calculates the inner product, dl over dx and dx, and the inner product between dl over dw and dw, and compute this expression and get this one, and compares these two values are approximately the same, whereas more specifically it is calculating the relative error between these two values, and say it is very small. And it repeats this computation 14 times with different random weights and random inputs, and computing the maximum relative errors and average relative errors. So in this case, the error was less than 0.1% was. So if these two values are both very small, then yeah, you will be okay. But if you somehow get the calculation of, for example, these values wrong, then yeah, so the relative error might be way larger. So this is how you might be able to catch some errors. So especially when you modify multiple layers, you may be able to easily shoot down which particular layer is wrong. So this is what I have already shown using the demonstration. So just for your note, this is what I have obtained by running all these standalone programs. So these are maximum relative errors and average relative errors for each of these layers. And SP stands for this single precision calculation, and DP stands for double precision. So the default implementation is single precision floating point numbers, but you can change it by changing this command line. So this time, so the parallel make again. So this time, double precision numbers are used for all the real values. And run, for example, convolution. Then, yeah, remarkably, the both maximum and average relative errors are exactly 0. So this is what you got here. But anyways, so except for max pooling layers, these errors are supposed to be very, very small. So there's a reason why for max pooling the error is inevitably large in some cases. But if this value is relatively small, as small as this, at least for double precision numbers, you will be all right. Also, sorry, this should be the average. So as long as average relative errors are as small as this, you'll be all right. So with that, I think I have explained everything I have to tell you at this point. So there's still some things are still under construction below, so which is a tool to submit your record, execution record, so how much time it took, and so that you can compare your result with others, and also PyTorch implementation, for example. So just to know where your code stands in terms of the performance. So details will be announced soon, but well, never wait for this tool to become available. So you should be able to get started with your work with the information I already provided. Also, more details will be announced about how you are supposed to submit your code and your report. So your report is going to be submitted through the ITCLMS, but your code will be submitted in some other ways. So whether it is Jupyter or whether it is to the GitHub, I haven't decided. So I'm gonna announce it shortly. But again, you don't have to wait for this announcement to be made for you to get started with your work. So with that, I think I will finish this video and have a good luck on this work.